Hey everybody, so this is going to be a video that focuses on the concept of neutralization and performing a titration. So neutralization, kind of like the name implies with neutral in the title, is the process of mixing an acid and a base together. Because the acid has the hydrogen and the base has the hydroxide, when that hydrogen and hydroxide come together, they form water. And we know that water has a pH of 7, which is neutral. Even just by kind of looking at this reaction, you might recognize this as a double replacement reaction. That's kind of like the basic mechanism behind what's happening when an acid and a base mix. The idea that you've got this, the hydrogen, the cations basically, switching places, and then producing your two products. You're going to notice that you're always going to get some kind of byproduct. We usually refer to that as a salt, or in other words, just an ionic compound. So yes, sodium chloride is salt, but by salt I just mean kind of any ionic compound as a result. We're only going to be doing examples with strong acids and strong bases because we know if they're strong, they completely form into ions and solutions. We know how many of those ions we're going to have, where if we have something that's weak, it's a little bit more complicated to figure out the concentration of those ions. So let's quick review total and net ionic equations, if that rings a bell. Remember, total and net ionic equations are another way to write out usually a double replacement reaction. Basically, as the name implies, it is an ionic equation, so it's more or less referring to the ions that are involved in the reaction. So as a reminder, you take anything that is aqueous and you actually write it separated, because if it's aqueous, if it's gone into the solution, it is formed into ions. So we're going to have that hydrogen ion. We'll have a chloride ion. Then moving over, we'll have a sodium ion. We will have a hydroxide ion. Then we've hit our arrow. We also have sodium chloride aqueous over here, so we'll split that guy up. And then we're hitting this liquid water. I'm going to rewrite it as H2O. It does not matter. Because that is liquid water, that is not going to form ions in solution. So that is just going to be the final compound at the end of the day. So you're really only doing anything that is aqueous. So that's your total ionic equation. That's the everything equation, if that rings a bell. Then what you do is you cross off your spectator ions. Your spectator ions are essentially ions that are present at both the beginning and the end, basically meaning they didn't go through a change. So in that case, that's going to be your sodium and your chloride. So after you get rid of your spectator ions, your net ionic equation is what you have left over. So in this case, it's an H, it's an OH, and it formed water. And that would be our net ionic equation. And remember, net ionic equations kind of are telling you what's actually happening at the end of the day. So that's like the actual reaction, the actual change that is happening. And if you'll notice, what we've got actually happening is you've got the hydrogen from the acid, the hydroxide from the base, and they are coming together to make your neutral water. And in fact, this is going to be the net ionic equation for every single acid-base reaction. Essentially because you're always going to have an H from the acid, you're always going to have an OH from the base, so you're always going to be making water as a result. Yeah, there's some other spectator ions or maybe some other things going on, but at the root of it, you should always be forming that water. So why don't you go ahead and give this one a shot. Go ahead and write out the double replacement reaction, and then write out the total and the net ionic equation that forms from it. All right, so I've got my balanced chemical reaction up top. I switched around the K and the H, making water and potassium sulfate. I've got my total ionic equation and then my net ionic equation. Notice how I've got OH and H making water. Notice I simplified it down because there was 2's in front of everything, so I just simplified it down to still have it be a 1-to-1 ratio across the board. If you left the 2's, it's technically like a 2-to-2 ratio, which is the same thing. So with this idea of neutralization, we can do something called a titration. A titration is the act of slowly adding an acid to a base or vice versa until you get the solution to be completely neutral, and then using that data in order to figure out the concentration of either that acid or that base you are titrating with. And the concept behind it is basically this. As we know, when the hydrogen ions and the hydroxide ions are equivalent, we know that it is neutral. That is what we call the equivalence point. So when you've got the same amount of hydrogen ions and the same amount of hydroxide ions, Basically, they can all nicely match up with one another to form water. We know that water is neutral and has a pH of 7. The reason that this works out so nicely is because we've got this nice 1-to-1-to-1 ratio. Basically, one hydrogen ion, one hydroxide ion forms to make one water as a result. So this equivalence point is when you've got equal amounts of H and OH. So the idea behind a titration is you don't have equal amounts of either at the beginning. You've got something that is completely acidic or something that is completely basic. And then what you do is you add either the acid or the base to that until you reach that equivalence point. So basically, if you want to think about it, you need to have the moles of both the hydrogen and the hydroxide equal to one another. So if you've got equal amount of moles of H and equal amount of moles of OH, you're ready to go. And if we're going to do a little deriving here, we know our molarity equation is moles per liter, right? How many moles are in a liter? So if I rearrange this really quick and get rid of liters, I've got liters times molarity equals moles, okay? So if I've got moles of hydrogen equaling moles of hydroxide, bear with me, could I not say the liters of hydrogen times the molarity of hydrogen equals the liters of hydroxide times the molarity of hydroxide, based on my idea that liters times molarity is equal to moles. Okay. If we simplify this even further, we have this equation below. MAVA equals MBVB. And one thing that I kind of want to emphasize is while the A's and the B's are nice for acid and base, really we're getting at the molarity of the hydrogen ions, the volume of the hydrogen ions, the molarity of the hydroxide ions, and the volume of the hydroxide ions. Basically, if you know the molarity and volume of, let's say, an acid, okay, so you've got like 2 molar and you've got 20 mils of it, right? Molarity and volume. And you titrate it, which is just slowly adding one to the other, and you slowly add 30 mils of base to it. And then it gets to its equivalence point and it gets to be neutral. Essentially, you can solve for the missing variable and you can solve for the molarity of the base. So you know if the moles of the acid equal the moles of the base, you're at equivalence, you're good to go. So basically you can kind of work your way backwards or forwards. You can kind of go either way with this in order to figure out what you would maybe need in order to reach that equivalence point. Because obviously, like if you've got easy stuff, if you've got 10 mils of a 2 molar acid and you've got like a 2 molar base, well, how many mils are you going to need? Well, 10, right? Like if they're the same concentration. But what this allows you to do is like, okay, well, what if this is like a 1.3 molar? Okay, how many milliliters do you need? It lets you kind of balance it out in order to solve for any of those missing variables. So let's go ahead and try this out. So let's say you had 50 mils of an unknown molarity of acid. Okay, so you've got like hydrochloric acid, and you have no idea what the concentration is, and you like pour out 50 mils of it. And you know if you add 56 mils of a 0.50 molar solution of sodium hydroxide, you neutralize it to a pH of 7. So you're like slowly adding sodium hydroxide to it, and once you've added 56 mils, it's neutral, pH of 7. And now you're curious what the molarity of the hydrochloric acid is. So let's do some solving. Remember, this is technically the hydrogen plus concentration, right? And this is technically the hydroxide concentration. So because both of these are 1-to-1 ratios, notice 1H to 1OH, it's kind of the same thing, but it's just a good thing to keep track of. So basically when I'm looking at this, I do not know the molarity of my acid. So that's what it's trying to get me to solve for. The volume of the acid was at 50.0 mils. So I had 50 mils of the acid. The molarity of the base that it gave me was this 0.50 molar. And the volume of that base is 56 milliliters. So now we can go ahead and solve for the molarity of that acid. So if I go ahead and divide by, oh my goodness, handwriting, by 50 milliliters, oh my goodness, 15 milliliters on this side, I can go ahead and solve for the molarity of that acid. So I'm getting 0.5 times 56 divided by 50. Looks like I get 2 sig-figs here. I'm getting 0.56 molar. So that would be the molarity of my unknown acid if I titrated with that known amount of base. One thing that I want to quick show you is another way to solve this. And really, no way is better than the other. So whatever you feel comfortable with and whatever what makes sense to you totally works. So what we can do is kind of use this idea that the moles of H equal the moles of OH. So I know this is what I've got of the sodium hydroxide, right? So I've got 56 milliliters of a 0.50 molar solution. And I know that liters times molarity equals moles. So the first thing I need to do is turn these milliliters into liters. So 0.056 liters, just divide by 1,000. And then I can do liters times molarity to get moles. So 0.056 times 0.5, I'm getting 0.028. Did I type that in correctly? Yep, cool. So that's how many moles of the hydroxide ions I've got because of that sodium hydroxide here. And I know that when I titrate and I get to that equivalence point, I know that these moles also need to equal the moles of H+. I need to have equal amounts. So I've got 0.028 moles of my H+. And according to the beginning, I had 50 milliliters of that hydrochloric acid. So I could divide this by 0.0500 liters. Turn it to liters from milliliters. And I'm getting 0.56 molarity for the concentration, which was my same answer from before. So really it does not matter if you want to kind of do it more of the stoichiometric way, or if you want to use the equation, they'll both get you to the same answer. So why don't you go ahead and try a couple and then check back in when you're ready. All right, so this first one, I just told you how many moles of the acid were neutralized. And then if you go ahead and say, well, if that's how many moles of hydrogen, that's how many moles of hydroxide I need, all you needed to do was use the molarity equation to solve for the molarity for that one. The second one, though, the trick here is this calcium hydroxide and the fact that there are two hydroxides within that compound. So the first thing I did is I just solved for how many moles of hydrogen were in the acid. I know that if that's how many moles of H+ there are, that's how many moles of OH- there needs to be. But notice this is asking for the concentration of the original calcium hydroxide amount, not the molarity of the hydroxide ions. And so since every calcium hydroxide yields 2 hydroxides, if I've got that many hydroxides, I need to have it to get back to the 1 calcium hydroxide, which is why I divided this by 2 to figure out how many moles of calcium hydroxide I had. So it's important to note the difference between hydroxide and, in this case, calcium hydroxide. So I divided it by 2 to get to the calcium hydroxide, and then I could go back and solve for that original molarity and concentration using the molarity equation. So now that we've got the math behind a titration, what's the actual execution? So basically, we keep talking about this equivalence point, right? So when moles of H equal moles of OH and you've got a pH of 7, well, how do you know when you have a pH of 7? How do you know when it's magically neutral? The way we use it is by indicators. There's a slew of indicators out there. The one that we're going to be talking about right now is called phenolphthalein. Phenolphthalein. It is clear when acidic and this hot magenta pink when basic and this really pale pink when it is neutral. That's when it reaches its end point, when the indicator starts to change color. So basically what you do is you have this thing called a burette, and it slowly adds your titrant into your analate. So that's what you're adding into. And basically you keep slowly adding it until you get this color change that we're looking for. And then once you've got the color change, you know you've reached the equivalence point, and then you can do all of that math. You'll see this more with burettes, but they kind of read backwards, which is a little funky. And we use burettes because they are very precise pieces of glassware, and you can slowly administer your solution because of it.